Okay. Up to this point, the problems that we are involving was in statics and also here in the strength of material up to this point. Those problems were, we could somehow, using the equilibrium equations, and find the support reaction and then eventually the internal forces. In reality, the problem is that most of the problem we have in the real world is not like that they have only 3 unknowns. Usually you are going to have way more than 3 unknowns. And from the statics, we have only 3 equilibrium equations. So if we get more unknown than 3, then basically we cannot do anything with the statics, with the knowledge of the statics. So today we are going to start to look at it. If we have more unknown than the equilibrium equation, how we can solve those problems. Up to this point, we couldn't. We just said, okay, we are going to learn how to do it later on. So here's just the method of how to do it. So today we are starting to look at the statically indeterminate problems. So from the statics, what we had was like, if I have a beam like this, so I have 3 unknown, it's going to be 3 unknown. And then I have 3 equilibrium equations. I can write sigma fx 0, sigma fy 0, and sigma fz 0. And then from here, I can find reactions or all the unknowns. So if I have something like that, I can use my statics knowledge and solve it and find whatever I need to find. Now, what if it becomes something like this? So, if I have here, I have 4 unknown and 3 equilibrium equations. So I cannot solve it. That basically it becomes indeterminate. So I have 1 more than what I need. What if I go ahead and make it even, for example, so if I go ahead and say, in this case, let's say something like this. So if I have something like that, then I'm gonna have even get worse. So I have 6 unknown and only 3 equilibrium equations. So up to here in the statics, we cannot solve either of these two. We can solve this because we have three. So we have three unknown, and we have three equilibrium equation. So this one we could do it. We can then do that. We cannot do that, and now we want to see how we can do that. So here, how we want to get the equations for that is that we are going ahead and say, in this case, I have two conditions. So I have one, that this is my object, and it has those unknown on that. So I have my three equations. I need three more equations, correct? Because I have 6 unknowns. Then I would go ahead and say, then under the loading that it has, so assume I'm going to just put some load on that to see what I can do. Assume there's some load on that, on either of it. So if there's some load on that, what's going to happen is that they'll give me 3 equations, and then I'm going to have the deformation of that beam. And then I'm going to have deformation equations. And then I use these two together to find unknowns. So basically what happens is that whatever I can get from the equilibrium, I get it. Whatever left, I will try to get it from the deformation. So how it deform, and then I go ahead and said, okay, if it deform in this kind of way, I'm gonna find it. And usually when we are dealing in the real life, it's going to be way more than unknowns that we have. For example, you might have in the case that you have only 3 equilibrium, and then you end up having, I don't know, even for example a large building, hundreds of unknowns. So you go ahead and bring out every single element and write the equilibrium equation for every single element, and then still you are going to need more equation, and whatever left, you're going to see how that beam deform, or how that column deform, and then use the equation from deformation to solve. Here, usually we are dealing with a very simple problem, but the concept is more important, and say, okay, how we are going to use the deformation equation to solve it. Any question up to here? It's going to make more sense when we look at the examples. So assume we have there's a wall here. And then I have two kind of So this green one is kind of like it's a tube or pipe. Sorry, the center of that is hollow. But the center of the blue one is going to be a rod. The blue one is kind of rod shape. So the length is L, the force is P. So assume the length of that we have is L. This is L. And the force I'm going to put on that, so I'm going to put the force of P here. Just going to push it in. So that tube has assume it has a tube, it says cross-section area of E2 and A2 and E2, and the rod has a cross-section of A1 and E1. So it's a parametric, but any of them can have the numbers. Doesn't matter. So for example, I can go ahead and say it's a 10 millimeter tube, or it's going to be, for example, 50 millimeter rod, and it's going to 10 kilonewton force. So what it wants to know that if I have these two and I'm going to push them, how much force either of these two elements going to tolerate. So that P is pushing these two. So how much of the P would be tolerated by the blue one? How much of the force would be tolerated by the green one? So if I can draw it, consider the rod one. So the rod is going to be look like this. That's the rod. Then we have the tube part. If I can draw it, I have it. The rod that is going to be. So this blue one is inside that green one. And then if I want to say that, okay, say here, that is a force P, and there's going to part of that handled by here, so it's going to be P1, and part of that will be handled by here, then a P2. So the amount is going to be on that. The question is that what's P1 and P2? One for P1 and P2. Now if you look at here, so the first one is the equilibrium equation. So if I want to write the equilibrium equation, sigma Fy is 0 doesn't give me anything, correct? So sigma m about any point doesn't give me anything either. Because if I assume the sigma m about that point, that's going to be 0, 0. So the sigma m and sigma fx is not going to give me anything. The only equation that I can use as an equilibrium is going to be sigma fx 0. So if I write the sigma fx 0, what I would get? Got the p is equal p1 plus p2. Correct? And nothing else I can get it from the sigma fy 0 or sigma m about any point. So I end up with two unknown, one equation. So that's all I can get from the equilibrium, one equation. But I need two. So I have to go and find the other equation from the deformation. So look at that shape. What deformation relationship I can write for that? Strain equation. We can't write the strain, but what else we can write? It's easier one. So look at here. If I start to push that, assume that's not very hard material and we just move here, correct? So what's the relation between the formation of the tube and the rod? If I push that up to here, what's the relationship between the formation of the tube and the rod? It's equal. So that's the relationship we look for. So we know that if I push it, both of them should deform equally. And that's what we look for. So we look for another equation. So basically what we look for is that we know that the deformation for both of them should be equal. So I will go ahead and say first for the rod. So the deformation for the rod is delta is PL over AE. So delta 1 is P1 L over A1 E1. For the tube, I can write the same thing, correct? Let me go ahead and say for the tube again, the delta is PL over AE. So the delta tube is P2L A2 over E2. Now the deformation equation. The deformation equation will tell me that delta 1 should be equal to delta 2. So if I go as I said that P1L over A1E1 should be P2L over A2E2. now I have two equations. So I have one here, and I have two here. Now I have two equations, two unknown, so I can put them together. So if I set this in 1 and 2, which gives me, assuming all of these are known, assume we know the P, we know the properties of the rod, we know the properties of the tube. The only unknown are P1 and P2, so we can find the P1 and P2. I said if there was a number, it's relatively very simple to calculate. So you see, now probably you can see it better. So here, when it says that we get what we have from the equilibrium, and whatever left, we go and look at the deformation to see what equation we can get from the deformation. For example, in this case, both rod and tube deformed equally. But they're forced to deform equally, let's say that. And then we can get that equation. Okay, let's look at another example. So assume we have like this, and there's a point A, point B, say L. Length, and there's a point C, somewhere here. There's a point C that there's a force P applying on that, and it's going to be at the lengths of L1 and L2. L1, L2. So we want to find the reaction of the support on A and B. Right. So if you look at that, I have two unknown here, two unknown there. Two reactions there, so 4 reactions. And because there is no force in the X direction, I said, okay, the X reaction, we don't care about it. It's only going to be the Y reaction. So if I go ahead and redraw that, what I'm going to get is this. So I have the P1 that's here. And then get both of them off. So I have a R at A, and I have the R at B. So if I go ahead and write the equilibrium equation, sigma fx doesn't give me anything, correct? Sigma moment about any point doesn't give me anything either. the only equation that I can use that gives me something meaningful is the sigma fy. So if I go ahead and say, okay, sigma fy is 0, then what it gives me is that RA plus RB is equal to P. The P, not P1. Correct. So RA plus RB is equal to P. That's all I'm going to get out of that. So I have two unknown, one equation. So I have to find one other equation to solve that, and I have to get it from the deformation. So what I can get from the deformation? What deformation equation or what deformation relationship? I can write it here. For example, here I said, okay, they both deform equally. What can I say about the deformation there?
B will deform more than A.
Let's make these points C. Say that again.
The point B will have more deformation than, so like from C to B will have more deformation than from C to A.
Okay, so assume that's correct, it still doesn't give us the relationship.
Yeah.
What about the total deformation here? How much the total deformation? Look at here. This bar is fixed between these two supports.
Mm-hmm.
So its length increase, decrease, or doesn't change?
Doesn't change. Doesn't change. I mean, it all.
If the support doesn't move,
yeah, then it doesn't change.
that doesn't change. So
There is no deformation.
there is deformation, but the total deformation would be, that's the part. So the total deformation is 0. Correct? So that's the relationship we look for. The total length doesn't change, but the AC length change or doesn't change? The AC part.
Stretch out. Yeah.
So
It will increase.
So the AC increase, at that increase goes where? What happened to the BC? Compress.
Decrease.
So the increase there and decrease, so if you look at the point C, the point C is not gonna stay there. The point C would come lower, correct?
Yeah.
But A and B would stay where they are. So the total deformation is 0, but the deformation in each part is not 0. Correct? You got that? That's very important. So we go for the deformation. If I want to go to the, I will write it for the AC. So if I write the delta for AC, so it's how much AC will be deformed. So I have to first of all to cut it. So I'm gonna cut it there. That's gonna be RA. And it's gonna be N, which is gonna be equal in this very simple one. The N, how much is gonna be the N?
P.
we don't know how it's gonna, we don't know how it's gonna do pieces, but we know it's gonna be equal to the RA. So N here is gonna be equal to RA. So now that I know that the delta for the AC is basically P in the AC, L of the AC, A and E. A and E is the same for all of them, so I'm gonna just leave it as it is. So the delta for the AC is gonna PS, which is gonna be RA, and then it's gonna be L1, A, B. Agree? So delta for delta for BC. So I'm gonna, this time, I'm gonna cut it from bottom. Okay, so I keep the bottom part of that, so B. There's the A. Now this time I'm gonna cut it from the bottom part, so it's gonna be so that's the point B, and then I have the RB, and then I have the usually you draw the N remember, N is always tension, correct? So how much is going to be the N here? Negative RB. So delta in the BC is going to be force in the BC, the length of the BC divided by area. So delta in the BC is going to be minus RB L2 AE. So this one compress, this one stretch. And now the deformation equation. So the deformation equation that I have, that I want to use just the deformation equation, the delta AB is 0. The delta AB, the total delta is 0. Therefore, the delta AC plus the delta BC is 0. So if I go there and say, okay, the delta AC is the RAL1 AE minus, or what is it, plus minus RB L2 AE would be 0. Forget that. So now if you look at it, I have two equations. I have the equation 1 here, and I have the equation 2 here. So I can use equation 1 and equation 2 find P1 and P2 or RA and RB. So any question about this? So one more time, very quickly. First we write all the equations we can get from the equilibrium. And then we see how many unknowns we have, how many equations we have. So in this case we have 2 unknowns, 1 equation. So we left with one more, we need one more equation. And we try to find that one more equation from the deformation. Look at here. We know that the AB is fixed, so the total length of the AB should be, the total change in the AB should be 0, but the change in the AC is not 0, the change in the BC is not 0 either, but the total is 0, so we go there, find the change for the AC, find the change for the BC, and said, okay, if I add these two together, it should become 0, so it gives us the deformation equation, and the second equation we can solve, use it to solve the problem. Question? So this is one method that we are solving the indeterminate problem. So go ahead, write all the equilibrium equation, and then write all the deformation equation, and then put them together to get the unknown. There's another method to solve the indeterminate equation, indeterminate problems. It's somehow similar. And it's called using the superposition method. Probably have it in different, for different things in the physics. Superposition method, how we can use that to find it. So first of all, what was the superposition? Remember it from physics?
Strings keep going.
Okay.
That's about as much as I remember.
So assume I have, so this is a determinate case. So assume I have the beam like this. And then I have two forces applying on that. F1 here, F2 here. And I know that it's gonna have some deformation, so it's gonna deform to something like this. I'm gonna exaggerate it, but I assume it deformed to that green line. And at the center, the total deformation is delta. Assume this deformation here. Okay, so I can go ahead and say, instead of us solving that, I can go ahead and solve and break it into two cases. It's equal to this and this. So I have I have one of them with the F1 and one of them with the F2. And then I go ahead and one of them with the F2. And then there's going to be, under F1, there's going to be the deformation. And under F2, it's going to be the deformation, right at the center. So that deformation, I'm going to call it delta 1. That deformation under, I'm going to call it delta 2. Let's call this delta. I can go ahead and say, you know what, like if I add these together, it gives me the original one. So in other words, I can say that delta is equal to delta 1 plus delta 2. So basically, I break the case into the simpler problem and find whatever I need to find, and then add all those simpler problems together. So that's the superposition method. So, any question about here? Now I can go ahead and say, you know what, I can use this logic and this method to solve a problem that involved with the unknown or indeterminate case. For example, something like this. So, for example, if I go ahead and say, you know, assume I have like this. It's the same thing, I just paint over because I want to show you what I mean. And the force P applying. I want to find the reaction of the support. So if I redraw that, it's going to look like this, correct? So how can I use the superposition method to solve that?
We could separate it into its two parts, I guess. So just the reaction between RB and P, and then just the reaction between RA and P, and see how the thing deforms separately for each thing, and then combine it.
That's correct, but so how do you separate them?
Just don't pay attention to it, I guess. You kind of neglect RA while you draw the RB.
So let's say this is correct. So I can go ahead and say I'm gonna break it into two cases. Assume I have the RA and I have the P, and this will cause some change in the length. Correct? So assume this length that it causes is delta. So this thing is going to be equal to this one. Now, what should I add here to make sure? So the plus. So what should I add here to make sure it's going to be?
Now you just had the other reaction, but you have the delta going the opposite direction, because it will be shrinking that time instead of extending.
So if I put the RB here, I would say that the RB should push it back to where it was originally, correct? So I said whatever the stretch the RA and P causes, the RB should counter it or cancel it out. So it should move it back to where it was. That's the superposition. So how do we do that? Usually we don't do it like this. How we are going to do that? We are going to say, okay, if this is the case that we have, it's going to be A and B. We're going to say this is going to be equal to, we get rid of one of the supports, so we are going to assume we are going to get rid of the B. Okay, this is going to be something like this. So it's only A and there's only P there. then it's gonna be plus. And the A is there. So usually we get rid of the reaction, one of the reaction, as soon as it's not there. And they said if it's not there, see what happened, and then if the reaction is there, should counter whatever happened without that reaction. So, how we do that again one more time. Remove the reaction, remove one of the reactions to make the case determinate. Solve it, and then remove all the forces but the reaction. And that reaction should cancel everything the other forces did. Got it?
Mm-hmm.
The concept of, we'll do it on the example so you see how it actually happens, but the concept of that, did you get it? So let's look at the example, see how we can solve this method. Again, I said we can use either of these methods to solve the problem. You can either use it like this or you can use it like this. Some of the problem would be easier to use this way, some of them would be easier this way. So let's assume we have something like this. 300 and 600 kilonewton. So this one is 300 kilonewton, and this one is 600 kilonewton. As point. D and K. Okay, if we have these, what do we look for? So we're looking for the reactions. So what's the RA and what's the RB? So if I want to do the superposition here, I have to eliminate one of the support. Which support would you eliminate? I have to make it, right now it's indeterminate because I have one reaction here, one reaction there, and it is just sitting on that surface, so it's just sitting there. It's not fixed support. It's sitting on top of that. Just sitting on top of that. So I have one reaction here, one reaction there. I have two reactions, correct? And it's only one equation of the equilibrium. So I have to get rid of A or B. Like that, so say, if I want to do the superposition, I have to get rid of the support to make it determinate, and then put the effect of support back on the case. So in this case, it's probably easier to go ahead and say, you know what, I'm gonna get rid of B, and I let it to stretch. So if I get rid of B, so what I'm gonna have is, I'm gonna have the A part. Just exaggerated a little bit. That's the A. And then I have this 300 here, and then 600 here. And it will stretch down. Call it delta L. So I'm gonna say it's stretched on equal to delta L. Agree up to this point? Yep. Now, if I want to make sure this is gonna be equal to this plus, so I remove the reaction. Now I have to put the effect of reaction back. So if I go there and say, okay, I'm gonna put the effect of reaction back, and so it's gonna be there, there. put the reaction of the RB back. And assume the RB will cause some deformation. How much is gonna cause the deformation is gonna be delta, right? So look at here, I get rid of the B. It's stretched as a delta L, correct? And then when I put the RB back, it should be pushing it back to its original location. You get, before I start to solve it, I want to make sure that you get what we are doing here. So it stretch out, you get rid of the B, so it will stretch out. And then the B should be cancel that stretch and bring it back to where it was originally. Got it? So first of all, we have to go ahead and find how much is going to be the delta, how much is going to be a stretch, and then we're going to see how much that is going to push it back. Sorry, I have to put that together here. That's the A, that's the point B, that's the point B, and that's the C, that's the C. So first of all, I want to see how much is going to stretch. So I want to find delta L. So how much is the delta L? If I want to find the delta L, I have to go ahead and cut these in all these sections. So I have to look at here. I have to find the internal force, the normal force here, 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 and here. Got it? So I have to find the normal force here. I have to find the normal force here. I have to find the normal force here. And I have to find the normal force here. Agree? So how much is the normal force here?
0.
Is it? Forget it. How much is the RA? No, in this case, the RA is 300 plus 600, correct?
Oh, yeah.
In this case. So, if I cut it from here and look at the bottom part, how much is good? N. I cut it and look from here to here. 900. So N is going to be 900 here. How much is the N here? If I look at it, the bottom part.
600.
You agree?
Yeah.
How much is it here?
600.
600. And how much is it here? If I just look at the bottom part. Cut it and only keep the bottom part.
0.
It's 0. Look at that. So forget about the top part. You cut it there and only keep the bottom part. So if I cut it from here and forget about this part, assuming I cut it from there, so the N pulling it up and 300 plus 600 pulling it down. So it's going to be 900. If I cut it here, N pulling it up, 600 pulling it down, so it's going to be 600. If I cut it here, N pulling it up, 600 down. And if I pull it here, nothing pulling it down, so it's going to be 0. You agree on that? So if I know that, so then the delta L is going to be delta in the AD plus the delta DC plus the delta CK plus the delta KB. Agree? So if I go here, so set the delta L, delta in the AD, the P is 900 kilonewton. So the P times the L is 150. Divided by area, which is 250, and E, what's the E? I use the E for now, I don't see it. And look at it, all of them is stretching, so all of them are gonna be positive, correct? All of them stretch it, so the tension, all of them is gonna be positive. So it's gonna be plus from the D to C, so it's gonna be 600 times 10 to 3 times 150 times 10 to negative 3 divided by 250 times 10 to negative 6 E plus the CK, again it's going to be 600 times 150 divided by 400 E plus 0. I'm just writing it so you know where it's come from. So that is the, if I remove the B, this is how much it would be a stretch. And if I have it right, if I have everything right, it should come out as 1.125 times 10 to 9 divided by 8. So I have the delta L, and now I have to find the delta R. So I know it's stretched that much. Now I know that RB should cancel that stretch because the total stretch is 0. So whatever is stretched, RB should cancel it. So I go ahead and say, okay, find delta R. So if for find delta R, how much is the N here? Minus RB. So N is minus because it's compressing it, correct? And the same here, if I cut it here, N would be agree? So now I can go ahead and find it. So here, if I want to write that the delta L, delta right, is gonna be the delta AC plus the delta BC, or CE in this case. Right? So the delta R is gonna be minus RB times the length, which is gonna be 300 times 10 to -3 divided by area, which is gonna be 250 times 10 to -6 divided by E plus minus RB 300 10 to -3 and divided by 400 times 10 to -6 E. So if I have it right, the delta R would be minus 1.95 times 10 to the 3 RB E RB. So now I know that for the deformation, or superposition part, I know that the superposition is that the total delta is 0, therefore the delta R, the delta L plus delta R should become 0. So now I have them, so I have 1.25, 1.125 times to the 9 divided by E should be equal to minus 1.95 times 10 to 3 divided by E. RB is 0, so the RB would come out as $577 kilonewton. If I have everything correct. You got it up to here? And how do you find the RA? Equilibrium. Sigma Fy is 0. So sigma Fy is 0. So what I have, assuming, let's see, assume both of them upward, so it's gonna be RA plus RB plus 300 plus 600. Oh. 600 should be 0. So our A would be 323 Newton. So just assume very quickly, just draw it very small here. Just assume the book assume both RA and RB are like this. So it's the RA, that's the RB, that is 300, that is 600. So any question up to here? So we could have done it with the previous method. We could have said, okay, find it this delta plus this delta plus this delta plus this delta and make it 0. In the previous method, rather than removing the B, just find the delta in each of them and say, okay, the total change should be 0 and just solve it. No, let's look at another example. See, you know what? So this time, like I have the very similar, just exactly same thing. That's the A. And this time, I'm gonna bring the B a little bit lower. So everything is the same, so it's the 250, it's 400, and it's gonna be the 300, 600. And And this time, this distance here, delta is equal to 4.5 millimeter. So now it's sitting above the surface for 4.5 millimeter. So the reaction of the support, if I want to find them, how do I find it for this case?
Total, which is gonna be plus 1.5.
Yep.
And you just solve the sigma.
So again, just get rid of the b. Assume the b is not there. So it's going to be equal to no b there. So it's going to be like this. So it's stretching all the way down here. So it's where it's originally is, where it's B and where it is right now. Right? And then I will put the B back. There's a B. So it comes down up to here. If I put the A, I go ahead and put the B back. So this time delta R is what? Delta R is this distance, correct? It is where it is originally sitting there. So it goes from here to here, delta R. How much is the delta left? How much is the delta? So the only difference from that case is that everything is going to be similar to the previous one. The only difference that you solve everything, but here in the superposition, delta is 4.5 millimeter this time. So delta R plus delta L would be 4.5 times 10 to everything is the same as here, except for that line. Except for that line, everything would be the same. The only difference is this line. This line is that delta left and delta right should cancel each other. Here is now the delta L, whatever is the stretch, that only cancel up to 4.5 millimeter of length. You got what happened here? Just can put the number in. Any question?